This morning, we're going to have a few lightning talks and then two not so long talks by Christophe and Audrey. But first, we'll start with Manuel, who's at the GFZ in Potsdam.
All right, everyone. Very happy to open up on such a nice day. So apologies in advance, this is not going to be extremely structured, but my work is on rock damage and healing. I'm going to pretty briefly describe an experiment to you and essentially just show you a bunch of results that we got. So the main questions we do have about those rock damage and healing phenomena is what we seem to consistently observe, at least in other experiments, are a phase of instantaneous damage in the form of a drop of velocity in the sample, and this being followed by sort of a logarithmic in time function of the wave speed in the sample that recovers its original level or near its original level. So we'd like to know a little bit more about the actual physics behind this. We do have a lot of empirical laws, but not really any satisfying predictive physical model of whatever's happening in there. On a lesser scale, we would like to find out if we could figure out some kind of scaling law in space and time for those recoveries, and even more specifically, if fluid in the sample does have any significant influence. Pretty sure that yes, but we'd like to quantify this. So our experiment, very briefly described. So this is our sample. We do have a bunch of transducers glued on it. This then goes into a triaxial loaded cell. We submit it to a 2 MPa confining pressure, and we just apply this load, very simple. So from 11 p.m. to about 6 a.m., we just, so this is the strain you're looking at. We just compress it, leave it there for a couple of hours, relax it, leave it there, compress, relax, and that's about all we do to our sample. And we do this up to about, the step height is about 50 microstrains. So what we're looking for is kind of a mixture of behaviors. So this, if this is the velocity in your sample during the experiment, this is what most people would expect, namely that we compress the sample, it becomes stiffer, velocity increases, you relax it, becomes softer again, decreases, increase, decreases. I actually made this the wrong way around, sorry about this. But what we're actually also looking for in terms of healing is that we're looking for those transients with those log time recoveries that happen basically every time we do anything, whatever, to our sample. So this is, I'm just going to show you a couple of things. So this is the direction of load. Those are two transducers, one of them acting as a source, the other one as a receiver. We just make active measurements, and what we do is we compare the waveforms all across the experiment, and we just compute the shifts, the time delays that we just compute basically time delays on the first arrivals in this case. And as you can see, so along the dotted lines here, every time we do something, it doesn't matter if we compress or if we relax, every time we have a softening of the material, followed by logarithmic recovery or logarithmic-ish, and this just happens every time, again, we do basically anything to our sample. But then, if we move on to a little bit more complex sensor configurations, because we do have 14 of them in the sample, then we start looking at a little bit more funky things. So this is a different time window. This is a different configuration of sensors who are both on the same side. So basically, what we're going to be looking at first is first arrival, a surface wave, and then if we look later on in the waveform, we get something like doesn't really look like anything, but then we filter something out, and ta-da, we get transients again. This frequency band, why is it this one exactly? We played around a bit and realized that this was actually working, and it turns out that those shift values are exactly twice the ones that we saw for the first arrival, so we're pretty sure that this is really the P wave being reflected and just arriving back on the sample. Then, if we look at other configurations, we can have a look at two transducers really opposite across the diagonal. Then we see something that's kind of a mixture of what I showed you at the beginning, namely those sort of like bulk changes in velocity, because as you can see, those transients are just moved up. So we compress the sample, everything sort of moves up, but we still get this transient, moves back down, moves back up, moves back down. So we get sort of a mixture. And then if we look at yet another configuration, so those are just two transducers that I've picked basically at random on my sample. And then this doesn't really look like much. Yet it's yet another time window in the trace. But then again, we filter it out and we manage to land back on free, sort of, and get something that looks like transients. And in this case, really, whatever's happening in the sample, we don't really have any idea. And that would be kind of the goal, to try and figure out what is it exactly that we're sampling whenever we do have a look at those active measurements, P wave arrivals. Maybe it's a mixture of P and S wave. What are transducers specifically sensitive to? What are the effects of the surface waves? Plenty of questions left unanswered. So that's why for the time being, we're just going to focus on interpreting our data for the simplest path. So really sensors facing each other and looking at the first P wave arrivals only. Then afterwards, we can explore, have a look, because we can compute the shifts basically anywhere in the trace, and have a look at what happens if we filter the signal, what happens if we change the geometry of the transducers, and then just really whatever we find, and then we'll try to explain afterwards, and then we can rinse and repeat all of this on our other data set where we have a fully saturated sample. Thank you.